Swayam Prabha. Digital India. Educated India.
So, in the last couple of lectures, we have talked about sound propagation in regular rooms and also in irregular rooms. In case of irregular rooms, we developed a parameter, reverb constant. And while developing this parameter, we had assumed that there is no damping in the air, but the walls themselves have some dampening effect and they do absorb some sound. The context of all this discussion, regular rooms and irregular rooms, is that if there is some sound which is getting generated in a room, how does it propagate? And it has direct applications in areas of, in places, in acoustic spaces, lecture halls, auditoriums, theaters, places where do the recording, even small rooms. I wanted to develop this reverb time further. And also what we will see today is what does air do to this whole notion of reverb time. But before I start doing that, I wanted to generate some thinking that if you have a, let's say, a big room, lecture hall, where you sit and take lectures and there are 200, 300 students sitting in the room, what are different things as an engineer you would think which will help you design a good lecture hall? So can you cite some parameters? They don't have to be very well defined engineering parameters, but what will make as a listener a good room and it will distinguish it from a bad room? No time delays,
speakers, bass and the sound reaching us.
Why should that matter? If the speaker generates a sound and reaches you after, in an absurd case, 5 minutes later, what does that do? Why is it bad or good?
It will lose the synchronization and the harmony.
But it reaches, first letter reaches you after 5 minutes, the second letter reaches you after 5 minutes plus some delta t.
That's right.
So
if you do not watch him, then it's okay.
Okay, understood. So there is no synchronization between his lip movement and understood. Okay. So okay, so that is one, that no significant delay between the sound source, I mean the time when sound is coming out and when it reaches your ear, because there will be a disconnect between visual perception and auditory perception. So that is one. Good. You wanted to say something?
Sir, there should not be any notes and in the room. The sound should be uniform all over the room.
Sound should be uniform all over the room. Okay. And why is that good or bad? Or why is that good?
I mean, if one person is sitting like this and if he changes his position, he should hear the same volume, like the same sound.
Second is that. Anything else?
There shouldn't be echo.
There should not be any echoes.
Yeah.
Why are echoes bad?
And we'll hear double sound like.
Okay. So echoes is there. Anything else?
So the main importance should be on the vocal frequencies.
Main importance should be on the vocal frequencies. Why?
The note for vocal frequency should be less.
In a lecture room.
Yes, sir.
But not necessarily in a place where you are playing music.
Yes, sir.
So it depends on the application. Yes. That how the room behaves should be tuned to whatever is the band in which sound is being generated. What about noise from outside?
Noise cancellation.
You want to minimize that. Noise which is coming from outside has to be minimized. Echoes you already mentioned. So we'll also cover some of these other things which we talked about.
There should be no resonance with the objects around.
No resonance.
I have seen many a times these chairs, and if it is especially metallic objects, they start to vibrate and make sound in the bassy room.
In the room.
If there's a loud bass,
yes,
objects begin to
yes,
chatter.
etc. Yeah. So there shouldn't be any buzz, chatter, rattle, creaks, these kind of things. So yeah, so we will cover some of these. We will definitely cover echoes. We will cover some criteria so that we can figure out what is a good acceptable noise level as it comes from outside. We will also cover a term called room constant. So we have talked about reverb time, and we will also introduce a term called room constant. So that is all. That is the spectrum things we will cover today. But we will start by including the effect of air damping on reverb time. We had seen that reverb time is 60 times V over 1.08 AC, right? A prime C. And we had defined A prime C as minus S natural log of 1 minus alpha. So what we will do is we will modify this particular equation by incorporating the damping generated due to air. Let's say D naught is my initial energy going into the system, and once sound travels a distance D, which we had defined in earlier lectures as mean free, then just because of air, this D naught, it goes down, and it becomes D naught e to the power of minus t, where m is fairly small compared to 1, and its dimension is 1 over length. The dimension could be of m is 1 over meters or 1 over feet. So using the logic we had used in our previous lecture, we can say that D, which is at the energy density at a given point of time equals n delta t equals D naught 1 minus alpha bar
To the
n e minus n md. This is after n reflections. This part, the one in yellow, is because of the reflections of the wall. This part is because of the roll of the air. So you have n reflections, so it's n times m times d. We know that, so we can develop this further. So that is d naught 1 minus alpha bar, and n is what? T over delta t, right? And then the other exponent part is minus, again I will replace n by t over delta t, so it is t times md over delta t. Now we know that d over delta t is what? D is the mean free
C.
path.
C.
It's C, right? Velocity of sound. So I'll put that in here. So I get d naught 1 minus alpha t over delta t e minus t m c. We also know that 1 over delta t is basically cs over 4v. We had seen this earlier. So I modify this further. D0 1 minus average alpha. So I get CST over 4v exponent minus t mc. So now what I do is, like I did for the earlier case, I express this entire thing also in an exponential format. So I get d equals d naught exponent. So I get log 1 minus alpha bar SCT over 4v minus t mc. And if I rearrange my stuff, what I get is exponent minus S ln 1 minus alpha bar plus 4 mv times Ct over 4v. I can make this whole thing as A prime air, because now it includes the effect of damping also of the air. So I get d naught e minus A dash air times Tc over 4P. So this is essentially very similar to the earlier expression we had developed for a room with no damping due to air. So I can use the same logic stream and I can say that reverb time, if I have to include the effect of air, is basically 60 times volume divided by 1.086 A dash air times velocity of sound in air. So couple of things. One is that M, this M parameter, which is, it actually very strongly depends on omega. So this depends on omega. And the relationship is that as frequencies go up, M goes up. So as omega goes up, we see through experimental data omega also, M goes up. So once again, we have to be careful that when we find a value of A prime, it's specific for a particular frequency or a narrow frequency band. It is important to understand. Second thing is that A prime air is approximately equal to A prime with for small values of for small rooms. If my V is small, then this term will pale in insignificance compared to the other term. So for small rooms, I may still get away with without including the effect of air damping. But for very large rooms, auditoriums, halls, it's prudent to use the damping effect. This completes the effect of air damping and what kind of an influence it has on reverb time. So does the reverb time go up or go down as I include the effect of air damping? It will go down.
Down.
Because this term goes up. And physically what it means is that what is the original fundamental definition of reverb time?
So the sound decays by the 60 decibel.
Yeah, which is a factor of 1,000,000.
Yes.
So it will take lesser time to decay to that floor level if I include the effect of air damping, which makes sense. So this completes our discussion on the reverb time. And now what we will do is we will move to a new concept, and this is also used in architectural acoustics, and it is essentially trying to develop a ratio of how much energy is received at the ear of the listener, which is directly coming from the source, and how much energy is coming from reflected, due to reflections. What we will discuss is SPL due to direct and reverb fields. I have my source, and then I have a person. Some energy is coming directly to the individual, direct, and some other energy goes, and it, as a consequence of reflections, it comes. So this is my reverb. The minimum amount of reflections, the reverb energy is what? Direct field, there is no reflection. The minimum amount of reflections which a reverb energy will have, will be one, at least one. Will see at least one reflection. In very large auditoriums, typically if you are far away from the source, in general the reverb energy dominates compared to the direct field. We will see that as we develop the mathematics of it. And the SPL depends on several parameters. It depends on volume, it depends on how far you are from the distance of the source, depends on power of the source, and it depends on alpha and a bunch of other parameters. So first we will do is direct SPL, direct field. So I have a source, this is my ear
Sir,
or microphone.
Sir,
Huh.
sir,
the reverb energy, how can it dominate? Sir, there will always be some.
We'll see that. And this is the distance between the source and the ear. I ear, which is the intensity at my ear. And let's say the source is emitting W watts of energy. So I ear is what? Based on some of the earlier concepts you had developed. Intensity is
So P.
power
Do you PU star?
per unit area. Right. So it's watts over 4 pi r square. And we know that we can also write this as P direct, the whole thing squared. I have to average this, divided by 2 rho naught, and I can write this in a short form over 2 rho naught C. So again note that PD is average RMS pressure. From this relation and from this relation, what I get is PD square is essentially 2 rho naught C times whatever is the strength of the source divided by 4 pi r square, or PD equals the square root of rho naught C W over 2 pi r square. So this is my first relation, and we will apply the standard disclaimer that this everything of this nature is valid to the extent my r is what?
Very less than lambda by 2 pi.
Yes. It's fairly large than 1/6 of the wavelength of the frequencies we are considering. So this is my direct. So now what I will do is I will develop something for the reverb field. We do it for a reverb field. So for the reverb field, you have to think how the sound develops in the room. If the room has absolutely no dampening surfaces and sound does not leak out of the room, then as my speaker is pumping energy into the system, what will happen to the reverb energy over a period of time? It will just keep on going on, increasing infinitely. If there is at least one dampening surface which absorbs some energy, or if there is air which is also absorbing energy, then the reverb field, the way it will behave is that it will keep on growing, but the rate of growth will start over a period of time, it will start slowing, and it will become flattened, it will flatten out. And after a certain point of time, whatever is being pumped in to the speaker is getting absorbed by the walls, and there is some sort of an equilibrium. So what we are trying to do in this analysis is that we are trying to find that what is that equilibrium state. So it's not the transient state. What we are trying to figure out is what is that equilibrium state at which the reverb field does not grow over a period of time. So in this analysis, what we will essentially do is we will compute whatever is going in, input power, and whatever is going out, which is the output thing. And once they are equal, then that is my condition for equilibrium. Input power equals what? What is the input energy going in the system, or power going into the system? It is
whatever is pumped by the speaker.
No, but it has to see at least one reflection that is going in. So what is that value? What is being pumped by the system? W.
W times 1 minus alpha.
W times 1. So this is power flow into the room. Now what we will do is whatever is going out. So power going out equals energy going out divided by time. Right. I will number them 1, 2. This is 2. Power going out is essentially power lost per reflection. So that is energy lost per reflection. And then what is the time? Time is delta t,
Delta T.
right? There is time between two reflections. So this is energy lost per reflection over delta t. And we know that delta t equals what? D over C, and it is also 4V over SC. So now dr, you define a term dr, it's reverb energy density, and that is essentially ER, uppercase R implying it's reverb pressure, RMS, the whole thing square divided by rho naught C square. Is from earlier notes. And ER is reverb energy in the room. So what is reverb energy in the room in terms of dr? Dr is reverb energy density. So reverb energy in the room is
into 4
So
plus.
into 4 S into delta T, sir.
this is energy density. Dr is energy density. Unit of energy density is joules per cubic meter,
Yes.
for instance, in SI system. So total reverb energy in the room is what?
Multiplied by volume.
Times volume.
Times volume.
Times volume. So it is dr times volume. So that gives me V E R dot RMS, the whole thing square over rho naught C square 3. And total energy lost each reflection will be how much in terms of ER?
ER into 1 minus alpha.
ER times alpha.
Here times.
Yeah, that's all.
Energy lost each reflection is ER alpha. So total energy lost per reflection ER times alpha, which is same as dr times V times alpha 4. So whatever is the flow going in, we know W1 minus alpha, and that equals whatever is going out. So now we equate them. We have to do one more step. This is the total energy lost per reflection. So total power which is decaying per reflection, which gets attenuated per reflection, or it gets deducted per reflection, total power will be how much?
So
This
W
into
times
time.
alpha.
Into time.
No. In terms of this, we know now we know what is energy lost per reflection is dr times V times alpha. So in terms of this,
Into time.
power
Delta T.
Upon
divided by
Divided
delta
by
T.
time.
So power loss, I will not say loss, power decay per reflection equals dr times V times alpha over delta T. And this equals whatever is going in, which is W times 1 minus alpha, right? So W times 1 minus alpha equals dr V alpha over delta T. And I substitute the value of delta T as Cs over 4V. So what I get is dr V alpha times Cs over 4V. And now what I do is this alpha bar, and if I use further this particular relation, dr equals PR RMS square divided by rho C square, and I plug in there, what I get is V times PR RMS square divided by rho naught C square alpha bar times Cs over 4V. So I do the math and I simplify this, and essentially what I get is reverb RMS pressure, which is averaged in time and space, the square of it is basically whatever the speaker is pumping in times 1 minus alpha over S alpha bar times 4 rho naught C. And now I introduce a new term called room constant, R. And R is S alpha bar divided by 1 minus alpha bar. And the unit of R is meter square or feet square. So ER RMS is basically 4 W rho naught C over R. So that's my reverb pressure. I'll read out these two relations. My reverb pressure is 4W rho naught C over room constant, and my direct pressure is what? Watts over 4 pi square times rho naught C. So what you see is that your reverb pressure does not change in the room, and your direct pressure very rapidly it decays with radius. So to answer your earlier question, if you are reasonably far away from the source within the room, the reverb pressure will dominate whatever you are going to do, and we will put some numbers on that. And my total pressure, and I can add the energies. Basically this is PR square is directly proportional to reverb energy, PD square is directly proportional to the direct energy, and I can add the energies. I cannot add the pressures themselves, but I can add the energies. So PT square is basically W rho naught C times 4 over R plus 1 over 4 pi R square. So this is the relation for my total pressure.
So this distance is minimum when we consider this a straight line.
Yeah.
So the part travel will be minimum.
Yes.
So in that case, the direct pressure will decay. So, and when we consider the reflected, then the distance traveled is more.
Yes.
So it will decay more then. So then how the
Yes, but the diffused pressure, the reverb pressure, it does not change from point to point. It will decay more. When you are in relative terms, see, all you are doing is you have to compare. You have to compare your direct pressure in a square way, 1 over R square way, decays as you move out. Your diffuse pressure is not changing within the space. The diffuse pressure is not changing within the whole room. So if you are fairly far away from the source, then your direct pressure will be fairly small, while the diffuse pressure will still remain same. This relation is basically addition of two energies. That is one thing I wanted to say. And this works only to the extent that both these sources are what, correlated or uncorrelated. We had talked about this earlier. The source of the music is uncorrelated.
uncorrelated.
And my sound pressure level basically 10 log 10 times PT RMS over E ref. Basically it's a square of this and square of this. So now I plot my SPL with respect to R, and the curve is going to look like somewhat like this. This is my R. R is the distance between the listener and the source, and this is my sound pressure level, and what I get is something like this. An asymptotic behavior where what is this value? This corresponds to
PD.
P what?
PD.
PD. This is my total PT. So PT converges to PD as I move away from the source. So this is not PD. I said that by mistake. This is reverb field. Another question that I know that room constant is S times alpha bar over 1 minus alpha bar. If there are no walls in the room, so that it's just I'm having a speaker in a field and I'm just running it, then what is R? What's the value of R?
Infinity.
Infinity. For if I am too close to the room, not to the source, then my direct field is dominating. Basically, that's what this relation is saying. And as I move further, there will be a threshold where this term equals this term, and once I have crossed that particular threshold, then the 4 over r term starts dominating compared to 1 over 4 pi r square. That particular value is where I have this equivalence between 4 over r and the other term 1 over 4 pi r square, that we call it r naught. So r naught is basically r square. Average size auditoriums. R naught is approximately equal to 20 feet. It's about 6 meters.
So R was 8 pi. So here it should be 2 pi r square.
4 WRC. And where is P direct? Okay.
2 pi r.
Yes. So R naught is about 20 feet for reasonably sized auditoriums. If I make my auditorium bigger, then this R naught also goes up because R goes up. And for small rooms, this is around 2 feet, less than a meter. So even in a room like this, most of the sound which you are hearing is essentially reverb energy, not direct energy. Consider a scenario where you have a recording equipment and there is a bunch of people who are creating some music, their instruments and all that. And if you are too far from the music, then the microphone will essentially capture the reverb field. If it is too close to the musical instruments, then it will capture predominantly the direct field. Now the limitation of capturing the direct field only is that each of these instruments, they have their polar patterns based on their geometry and all that. So if you are too close, then based on each instrument's polar pattern, the microphone will pick selectively some frequencies more than other frequencies. So that will not necessarily be a faithful reproduction of the sound. If you are far, then you do not capture that, but essentially what you are doing is you are picking up peaks and nulls, and you are picking up a lot of information contained in the modes and the natural frequencies of the room. So again, that distorts the faithfulness of the music reproduction.
And also, sir, if we are far, the absorption of the air absorption will be more.
Air absorption, but that you can amplify. But yes, air absorption.
And it is dependent on the frequency.
It depends on the frequency, but a lot of times these rooms are not that big. Recording studios are not that large. But yes, I mean, if you want to do this recording and sitting in the auditorium and where the performance is happening on the stage, and then air effects will also become dominant, will become prominent. So that will also curtail some of the higher frequencies. So it's very difficult to reproduce live music. Whatever you hear in a room when live music is being played, faithfully capturing that on a CD or a DVD or a cassette, it is very difficult, and there are technical reasons behind that. So it's not that the companies don't know what they're doing, but it's difficult. So a lot of times they try to put their recording instrument at this value or not. So it is like some sort of a compromise. Other thing is that we know that room constant is 4 W rho naught C over R. No, I'm sorry, PRMS. Right. So this is my room constant. So as room constant goes up, as it goes up, my P goes down. And so if I have a larger room, my reverb energy will go down in that room. Now we know that R is S alpha over 1 minus alpha bar. So what that means is that as alpha goes up, what happens to R? It goes up or down?
Sorry, first is, sir, depends.
Alpha is always less than 1.
R goes down.
Increases.
R goes up. So as alpha goes up, which means the absorption coefficient of the room is going up, R will go up and P will go down. More sound is getting absorbed, so less reverb energy. Similarly, as S, which is the surface area of the room, goes up, R goes up and P goes down. I just wanted to curve. So first thing I wanted to show in this overhead is that what you are seeing here is the dependence of alpha on humidity, which we have not explicitly talked about in earlier lecture also. But if I increase the relative humidity in a room, then my alpha, it actually decays. From 10 to 20% it goes up as I move from 10% relative humidity to 20%. But after that it goes down significantly. So humidity is a very important parameter as we are trying to figure out what is the value of alpha, and that has an impact on the time constant of the room. And what this is showing is that, so as alpha changes, how does room constant change? And this is also plotting the value of, for larger rooms, as alpha goes up, we expect room constant has to go up, and as alpha, as V goes up for a given value of alpha, room constant is growing almost linearly, and as I reduce my alpha, those linear relationships, they just move in parallel. The other thing is, so we will again start again from this relation, or actually we will start from this relation, and we will go further. So SPL is 10 log 10, and we had seen this rho W rho naught C times 1 over 4 pi r square plus 4 over r. This whole thing divided by E ref square. So now I can break it, and that is essentially 10 log 10 of W plus 10 log 10 of rho naught C plus 10 log 10 of this bracketed term, and if I also take the log due to this P ref, I get a value of 94. P ref is 2 times 10 to the power of minus 5. So I take that log and then multiply it by 10, I get 94 dB. Now we know that, like SPL, we had also shown earlier that PWL, decibels in power, is basically 10 log whatever the power is being measured divided by reference power, and that reference power is 10 to the power of minus 13. So if I plug this back here,
Minus 9.
minus 9,
Reference power, we usually take minus 10 to the minus 9 volts.
I think this is fairly standard. We'll check that.
10.9 is for intensity.
10 to the power of minus.
9 is for intensity.
So the story will not, because that's a number. So if I plug this back in here, basically what I get is SPL equals PWL plus 10 log this number, I mean this bracketed term, and then I get another some constant term, and that constant will change whether I am going to SI units or I am going to feet pounds system. But essentially it's PWL plus 10 log this whole bracketed term, and this C is 0.5 dBs for British system, And why I am talking about British system is some of the curves which you will see have charts which are based on British system. But for SI system, this is, what is that, minus 36. But anyway, so for British system, this is what you have. Okay. So if I plot the relative SPL, then essentially what does relative SPL mean? That I normalize it with respect to W itself. Then relative SPL is essentially dependent on 10 times log of this whole bracketed term plus this constant 0.5 dB. My reference, relative to this W. So what I wanted to show you was this particular chart. So what you are seeing here are relative sound pressure level in decibels, for which we had developed the relation just now. And here you are increasing R as you move away from the source. And then what you have are different curves. So for R equals infinity, which is open air, you have a straight line. Okay. Now let's consider this, and essentially what it shows is that, let's say, minus 20 dB line, and let's say I am only 2 or 3 feet away from the source. If I am just 2 or 3 feet away from the source, then the relative sound pressure level is fairly close to whatever I have for a room which has no walls, because this point on the curve is fairly close to this R equals infinity line. Do you guys get it? But as I move away, depending on what is the value of room constant, my sound pressure level starts becoming constant, and it is significantly different from R equals infinity line. So just wanted to show how R plays an important role in these calculations. That's what this chart I show you. For instance, for this 1000 R equals 1000 line, when I am at 20 feet, then I am here, where it is, the relative sound pressure level is fairly constant. But if I, for the same curve on R equals 1000, when I get closer and closer, and let's say I am only 2 feet away, then this point is very close, this point is very close to an open room response, room with no walls. So the next thing I just wanted to talk about is echoes. And there is some sort of a standard definition for an echo. What is an echo and what is not an echo? I mean, intuitively we all know that whenever sound gets reflected, it is an echo. There is a source which emits sound, it gets reflected, comes back to the listener's ear. If the delta T between the original sound and the reflected sound when it hits the ear is less than 15th of a second, then the perception of echo is not that great. If it exceeds 1/15th of a second, then you say, oh, there's an echo. There's some sort of a quasi-engineering definition. So it's like 1/15th of a second. If it is delta T is greater than 1/15th of a second, then you say that there's an echo. Now in fairly large auditoriums, not even large auditoriums, even in moderate sized rooms, you hear this echo. In auditoriums where the reverb time is in several seconds, echoes will be there, and they are always there. But the impact these echoes they have on our understanding and perception of the sound, it not only depends on whether the ear is hearing the echo or not, but also it also depends on how strong is that echo in terms of SPL. So if the difference of original sound and the echo's SPL is significantly large, then even though that echo is there, it does not have a very strong adverse impact on our assessment of the large room. So in that context, I wanted to show you another chart. So what you are seeing here is echo delay in milliseconds. 1/15th of a second is about 67 milliseconds. 67, 70 milliseconds. So on the horizontal axis you have echo delay in milliseconds, and on the vertical axis it is echo intensity in decibels, and this is relative to the original sound level. So if echo intensity is equal to original sound level, then what is the dB level difference between the two? 0 dB. So a 0 dB line will be just on the top of the curve, on the graph. So, and then you have different curves here. So we'll take one point. Let's say a delay of 100 milliseconds minus 10 dB of a difference. So let's say this is minus 10 dB of a difference. So that falls on the 10% curve. What that means is that out of every 100 people who listen to an echo where the delta t or delay time is 100 milliseconds and the echo intensity is 10 decibels less than the original sound, 10% of the people will get confused. 90% will be fine. Actually, it's the other way. 10% will be fine. 90% will get. Why is it the other way? No, 10%. 10% will be. 10% will get confused, and 90% will be fine. Now, if I increase the intensity level, then I have a 90% curve, and the decibel level is over 0. So I don't know how they constructed above 0, but essentially as you increase the decibel level of the echo, more and more people get confused. So this also gives you some approximate idea how to ensure that whatever echoes you are hearing in the room, they are below a certain threshold, so that most of the people do not have a poor view of the sound in the room. And then the last one is noise background. Okay. So the noise background could be, for instance, in this room, there's some fan running in this podium. There's some noise coming from this fan source. It could be due to, there may be power generator in the room or outside the room. It could be an air conditioner. It could be AC ducts sending in air. It could be people walking outside the auditorium. It could be traffic. So there are so many sources of noise. And there are again some fairly good guidelines what kind of a noise level is acceptable, because you cannot eliminate the noise absolutely, and what is not acceptable. So to do that, if you go by the Berneck book, what it says is that you have two steps. So step 1, identify what is your need. So identify this parameter SC, and SC is speech communication speech communication number. And there is a chart, we will show that chart. So for a broadcast studio where you have a person speaking or a musical instrument playing, and that is being broadcast over a wide range, that number is very low, because you need very little amount of noise coming in from outside. For a factory, that SC number is fairly high. So for instance, so again, for broadcast studio, that SC criteria, you have to, the SC number is 15 to 20. Then you go to music rooms, it goes up to 25. Then you go to a conference room where people also chat while they are listening and participating, it still remains 25. Then courtrooms, libraries, small private restaurants is 45, noisy. Factories are very noisy, so it could be anywhere between 40 to 65. So that is step 1. Figure out what is this SC criteria curve. And then in step 2, then what you do is you refer to another table and you identify max SPL levels. For each frequency or for different frequency bands. You figure out what are the frequency levels which are permitted. And this curve helps you do that. So suppose you are in that broadcast studio, you pick up this curve, SC equals 20. Okay. And you say, oh, my range of frequencies which I am going to use in this room are 300 to 10,000 hertz. So my SPL, noise coming out from the outside or unwanted sources, has to be below this dark line. So it's fairly straightforward. But these are like some sort of guidelines. Now, there are also dashed lines on this curve. And the only time you use those dashed lines is when all or most of your noise is in this 300 to 4800 band. If your noise content is also in this particular band below 300 hertz, then you stay with the dark line. But you can use this dashed line if most of your noise is above this 300 feet. Basically what it means is that since most of your noise is coming in that higher frequency range, you can have lower noise floors for lesser frequency. So that's it. There is some qualitative measures which you can use to design sounds. So we have talked about reverb time, we have talked about direct and reverb energy densities and how it relates to Hall characteristics. We have talked about room constant. We have addressed the role of echoes, extraneous noises, and in the next lecture we'll try to cover some applications of whatever. We'll definitely not introduce new topics. We'll try to cover some applications. And you had mentioned
Speech recognition.
Recognition.
speech recognition.
Not exactly speech. Sound recognition. There are overtones and many things which add to a particular note from a particular instrument.
Yeah.
So what exactly is that criteria which distinguishes one instrument from another?